Okay, so the next thing we're going to talk about are catalysts. Catalysts you've seen before, but we haven't talked much about. So you used one when you took hydrogen peroxide and it was decomposing to water and oxygen. Now in the store you're going to find hydrogen peroxide. It comes in a brown bottle. And the reason for that is it reacts with light. So light gives that decomposition extra energy and it happens a little faster. In order to prevent that, they close it off with light. Now you did it such that it naturally decomposes, but you found that let's see, putting in energy, so it's okay, so it's a reaction that looks like this on the energy scale, right? Well, catalyst comes in, you added manganese dioxide, and what the catalyst did was it lowered the activation energy. So, instead of needing all this energy to get going, a catalyst comes in and makes it easier for those particles to get together. It's kind of like a bridge, or a helping hand, or a matchmaker, you might say. So a matchmaker says, hey, you guys ought to get together. Or, in this case, you really ought to break it apart, because it's just not working out here. So, it breaks it apart, it lowers the activation energy, and therefore, what does it do to the reaction rate? It makes it a lot faster, which is nice, because you don't always want to wait around a day or 2 or 30 days for the whole thing to go, right? You just throw in the manganese dioxide, and whoosh, there it is, in a couple of seconds. Yep.
There's a product that my grandparents make called Dakin, and they have it in a brown container also.
Yep.
So that would be also something that relaxes sunlight.
Probably, yes. Okay. And this one is called chemical equilibrium. And equilibrium is just simply a balance. So you could think of it as a teeter-totter. And usually we have it as reactants on one side and products on the other. When they are balanced, it's at equilibrium. Okay? So your book talks about how you might have a vessel with a bottle with a cap on it, and you have some water in it, and the water's evaporating, and so you have water vapor above the water, and sure enough, some of that water vapor goes back into liquid. So that's a physical equilibrium. We're talking about a chemical equilibrium, where not only are reactants going to products, but products are also going to reactants just as quickly. So normally we think, okay, so we had our reaction, okay, H2 plus O2 goes to H2O, right? So we have our happy little reaction that way. And we always think, okay, it's just going to go that way. Well, eventually, in a lot of chemical reactions, there's a pushback where it starts to go the other way. And water breaks apart into hydrogen and oxygen. Now, with a really nice reaction, you're going to find that, 90% or so is going to end up as a product. And only 10% will stay as reactant. But sometimes it's as low as, 40%. And so what do? You want to affect that equilibrium as much as possible so that you can shift it the way you want it to go. Alright? And how do chemists affect the equilibrium? Well, they have a variety of methods, and a lot has to do with, once again, the environment that it's in. So, ways that you can affect it, we can go back to temperature. So temperature affects not only the rate of reaction, but it also affects the equilibrium. So let's go back to, we had, magnesium plus oxygen yields MgO, right? Okay, and we also said that gives off light, and that gives off heat, correct? Yes? Right. Okay, so what would happen if we increase the temperature that reaction is happening? We get more of the product. Why? We get more of the reaction? Okay, well, let's take a look at this. This was a overall what type of reaction? Exothermic or endothermic? We decided that this is an exothermic reaction, right? So overall, it's giving off energy, right? It's giving off energy. Well, what would happen if we're increasing the heat that this reaction is taking in place, yes? The whole reaction, where the whole reaction is taking place. What's that? Then it would be endothermic?
No. It would still be
We have heat as a product, right?
Yes.
And we say that going in this direction, we have an exothermic reaction.
Yes.
Right? If we're increasing the heat, that gives us even more product. Alright? And so what happens if we increase the heat, then that's going to push us more towards the reactant side. So anytime we push on the system, it's going to push in the direction that's most effective. So since heat is a product here, and it's an exothermic, it's going to push back towards the reactant. Okay? So temperature will affect the balance of a system depending on whether the system is exothermic, endothermic. Okay? Which way it goes. Let's try another one. Besides temperature, okay, that works good. Besides temperature, we can talk about pressure. Chemical equilibrium is going to be affected by pressure as well, based on what's going to relieve the pressure. And of the three substances that we talk about, gas, liquid, solid, which one of these is going to be affected by temperature the most, pressure the most? Why gas, Mung?
Because it has gas, but it expands, contracts with heat, and
it expands, contracts the most, right? So you try to put pressure on liquid, it's not going to compress very much. You try to compress a solid, it doesn't compress hardly at all. Gas is going to be easily compressible, and that's why you can put a whole bunch of gas in these gas tanks. People walk around with their carbon dioxide, their nitrogen, or their scuba tanks. They can compress gas easily. All right? So let's take a system where we have... Okay, so you took zinc, and you added it to hydrochloric acid, and you made zinc chloride, and gave off hydrogen gas, which you then burned in a tube, right? And it made a little barking sound, woof! Right? So zinc was the solid, and the hydrochloric acid was a liquid, and the zinc chloride was a liquid, and the hydrogen was a gas. Yes? So what would happen if you increase the pressure on the system? Which direction would it go to relieve the pressure most? It would go further to the right, because you're able to compress this gas. Yes? It can't go this direction as well as it can go this direction and relieve the pressure, less pressure that way. Alright, let's try another one. Besides pressure, you have concentration. So this one's a fairly straightforward one. So we can go back to our zinc and hydrochloric acid. Right? So let's say this only goes 40% to zinc chloride. And we want to make more zinc chloride. But once we have 40% zinc chloride, it starts to push back. The question is, how do we get it to keep going forward instead of pushing backwards? And the answer is, well, we can decrease the concentration of zinc chloride. So if we decrease the concentration of zinc chloride by removing it as it's made, then it will continue to push forward, and we'll change the equilibrium that way. But if we leave it in the reaction tank and it just stays there, then it's going to start to push back in that direction. Does that make sense?
No. Yeah.
Or what we could do instead is increase the concentration of these guys to push it more in that direction. So by changing concentrations, we can affect the balance from left to right. All right, I think that's it here.